Look out of an airplane window at cruising altitude. Beyond that thin pane of acrylic glass lies an environment far more hostile than the summit of Mount Everest or the deepest winter in Antarctica. The outside air temperature routinely plunges to -60 degrees Celsius, -76 degrees Fahrenheit, an intensity of cold capable of freezing exposed human skin in less than 2 minutes. Yet just inches away on the other side of that aluminum wall, you are sitting comfortably in a light sweater or t-shirt, sipping a warm beverage, completely insulated from the lethal deep freeze outside. The way modern jet airliners conquer this atmospheric freezer is one of the most elegant, unexpected, and efficient triumphs of thermal engineering in human history. Most travelers take cabin climate control entirely for granted, assuming an airplane uses massive electric space heaters or burning fuel furnaces like an apartment building or an automobile. In reality, carrying heavy dedicated heaters would waste precious weight and fuel. Instead, aviation engineers turned a potential problem into the ultimate solution by recycling one of the most violent byproducts of jet propulsion: extreme heat. The warmth keeping you cozy in your seat actually originates deep within the belly of the fiery jet engines hanging beneath the wings. To understand how an airliner stays warm, you have to look at the physics of a jet engine. A modern turbofan engine is designed to inhale thousands of pounds of freezing, thin atmospheric air every second. Before that air is mixed with jet fuel and ignited in the combustion chamber, it is forced through a series of spinning titanium and nickel blades known as the compressor stages. As the air is compressed into an ultra-dense volume, basic thermodynamics takes over. Compressing a gas dramatically raises its temperature. By the time the air reaches the final compression stage, it is burning hot, often exceeding 200 degrees Celsius to 250 degrees Celsius, 400 degrees Fahrenheit to 480 degrees Fahrenheit, long before a single drop of fuel is ever burned. Rather than letting all of that compressed thermal energy escape out the back of the engine as thrust, engineers divert a small fraction of it through high-pressure pipes. This tap stream is known in aviation as bleed air. Bleed air serves as the lifeblood of the aircraft's environmental control system, ECS. It is completely sterile because it is drawn off before the combustion chamber, meaning it contains zero exhaust fumes or burning fuel residue. This superheated air is then piped directly into the fuselage to perform two vital missions at the same time: pressurizing the cabin so you can breathe, and providing the raw heat necessary to combat the freezing temperatures of high-altitude flight. However, raw bleed air is far too hot to pump directly into a passenger cabin. Blowing 200 degrees Celsius air onto passengers would instantly turn the cabin into a sauna. To make it breathable and comfortable, the air must first be cooled down. It is routed into specialized units in the belly of the plane known as packs, or air cycle machines. The packs use heat exchangers to mix the scorching engine air with scoops of freezing outside air, rapidly dropping the temperature. The system then compresses and expands the air through an internal turbine, acting like a high-speed air conditioner that cools the air down to whatever precise temperature the cockpit pilots or flight attendants have dialed into the climate controls. Cooling and heating the air is only half the battle. The aircraft must also prevent that precious warmth from escaping back into the sky. An aluminum aircraft skin is an exceptional conductor of cold, which means without protection, the metal would instantly sap the heat from the cabin. Hidden directly behind the decorative plastic interior panels of the cabin walls are thick blankets of specialized fiberglass and hydrophobic insulation. These insulation packs prevent thermal bridging, block the deafening roar of the engines, and stop condensation from freezing into sheets of ice along the interior structure of the fuselage. One of the most widespread myths among airline passengers is that cabin air is stagnant and stale. In reality, the heating and ventilation system on a commercial jet completely refreshes the entire volume of cabin air every 2 to 3 minutes, far faster than any modern office building or hospital operating room. Roughly half of the air entering the cabin is freshly conditioned bleed air straight from the sky, while the other half is recirculated cabin air drawn through industrial-grade HEPA, high-efficiency particulate air, filters. These hospital-grade filters capture over 99.9% of microbes, bacteria, and viruses, keeping the atmosphere both thermally balanced and exceptionally clean throughout long-haul flights. While traditional bleed air systems have kept generations of airliners warm, newer aircraft architectures are moving toward an even smarter approach. The Boeing 787 Dreamliner, for example, largely eliminated engine bleed air from its environmental system. Instead, the Dreamliner uses dedicated external air scoops on the belly of the fuselage that feed fresh air into high-efficiency, electrically driven compressors powered by massive engine-mounted generators. This no-bleed design reduces drag on the engines, improves fuel efficiency by several percent, and gives the onboard computers ultra-fine control over cabin, humidity, and temperature zones without siphoning power from the engine cores. Have you ever noticed that you might feel slightly chilly in the front of the plane while someone in the back is complaining about being too warm? That is because modern airliners split the cabin into distinct temperature zones. The cockpit, first class, and different sections of the economy cabin each have independent temperature sensors. The environmental control system uses trim air valves to inject tiny bursts of warm air into specific ducts, constantly balancing the heating based on how many human bodies are sitting in that specific section, because several hundred warm passengers naturally radiate a surprising amount of thermal energy on their own. The heating system isn't just for passenger comfort, it is a critical tool for survival. When an airplane descends through clouds containing supercooled water droplets, ice can rapidly accumulate on the leading edges of the wings and engine cowlings, disrupting airflow and destroying lift. To prevent this, hot bleed air is ducted through internal channels inside the leading edges of the wings, keeping the metal surfaces warm enough to melt ice on contact. In areas where running hot air pipes is impractical, such as the cockpit windshields or pitot tubes, powerful electric heating elements are embedded directly inside the glass and metal to guarantee they remain ice-free at all times. The next time you settle into your seat, feel the gentle warmth of the overhead air vent, and look out over the frozen wing into a negative 60 degrees Celsius sky. Remember the invisible symphony of engineering happening around you. From the extreme compression heat of the jet engines and the precise cooling cycles in the belly packs, to the insulated blankets and zone sensors along the fuselage, modern aviation has transformed the deadliest cold on the planet into a smooth, cozy ride across the sky. This seamless mastery of extreme temperatures underscores a broader philosophy that defines modern commercial aviation. The most vital engineering achievements are the ones passengers never notice. When you sit in a pressurized cabin, enjoying a warm meal while cruising through a near vacuum that could kill an unprotected human in seconds, you are experiencing the culmination of more than a century of thermodynamic innovation. The ability to harness the raw, violent energy of jet engine compression and refine it into a gentle, life-sustaining climate is nothing short of an industrial miracle. It turns what should be a terrifying survival challenge into a background detail, allowing millions of travelers to focus on their movies, their work, or a quiet nap while traveling at nearly the speed of sound. Furthermore, this complex thermal balance serves as a constant reminder of how interconnected every system on a modern airliner truly is. The engine doesn't just push the plane forward, it powers the generator, pressurizes the hull, and heats the air. The fuselage doesn't just hold the seats, it acts as a high-tech insulation shield, a structural pressure vessel, and an aerodynamic fairing all at once. Every component is designed to do double or triple duty, maximizing fuel efficiency while maintaining absolute safety margins. The fact that an airliner can fly out of a 40 degrees Celsius desert runway in Dubai and climb into a negative 60 degrees Celsius troposphere 20 minutes later without the passengers ever having to adjust their sweaters is proof that we have mastered the physics of the sky. Understanding the invisible systems that keep us safe and comfortable makes every flight feel like a marvel of human ingenuity. If you love uncovering the hidden physics, engineering secrets, and mechanics of modern flight, make sure to hit the subscribe button and join our community at Aero Explained. Safe travels, and we will see you on the next flight.